JMB, how are you all? I hope you all are great. Welcome back to my YouTube channel. My name is Prince Ranpara. I'm a PhD scholar in the Department of Chemical Engineering at the Indian Institute of the Technology, ROPA. So in today's lecture, we are going to understand the engineering conclusion for the first order reaction kinetics, right? So let's get started. So in the previous lecture, where we have started the industrial numerical example, right, where we have considered the first order reaction kinetics by keeping all operating parameters to be constant, right? We have used different reactor models, the different reactor models like CSTR, peg-bed reactor, plug flow reactors, and the batch reactors. Okay, and we were trying to analyze how large volume of the reactor we required, right? How we will design the volumes of the different reactors, right? What will be my reaction time? What will be the space time? Okay, how much weight of the catalyst we required in order to achieve the desired conversion, right? How large volume of reactors we required in order to achieve the desired conversion, right? So all of these things we have discussed in the previous lectures, right? In today's lecture, we are going to understand the engineering conclusion for the first order reaction kinetics, right? Where we have a single reaction where reactants A are getting transformed to the new product B, right? We have kept all the operating parameters to be constant, okay? And we are solving for the first order reaction kinetics by using different reactor models. The different reactor models, right? CSTR, plug flow reactor, batch reactors, and peg-bed reactors, okay? And we are trying to understand in detail, right, like how large volume of the reactors we required in order to achieve the desired conversion of 90%. What will be my space time or the reaction time, right, in order to achieve the desired conversion of 90%. Okay, we have also understood that how much weight of the catalyst we required in order to achieve the desired conversion of 90%, right? So in today's lecture, I'm going to make you understand the engineering conclusion by doing the comparative analysis between different reactor models, CSTR, plug flow reactors, batch reactors, and peg-bed reactors, right? And we'll have detailed explanation, right? So let's understand that. So let's get started. So in today's lecture, I'm going to make you understand the engineering conclusion for the first order reaction kinetics, where we have the given rate law as minus RA is equal to KCA, right? And we have used the second form of CA, which is CA is equal to CA naught into 1 minus 6A, which also represent the fundamental relationship, and it is also defined as the conversion, right? Okay, now, okay, in order to make you understand in the detailed comparison between the different reactor models, okay, remember that we have kept all the operating parameters to be constant, right? Okay, and we have used different reactor models in order to analyze and design the volumes of the reactor, right? So first reactor model, so we'll make the detailed comparison between the reactor models, different types of reactor models, right? Like CSTR, continuously starting reactor, PFR, plug flow reactors, batch reactors, and PBR, peg-bed reactors, right? So we are going to make the detailed comparison between the reactor models with the volume of the reactors and the reaction time. Okay, so let's understand that. The first reactor model is CSTR, right? So CSTR, so in the previous lecture, we have understand the fundamental principle of the CSTR, right? So in CSTR, where we have the initial, where the concentration of the reaction environment equals the concentration of the outlet stream of the CSTR, right? Okay, so the concentration of the reaction mixture should be equivalent to the concentration of the stream leaving through the outlet stream of the peg-bed reactor, right? It is termed as the continuously starting reactor. Okay, means the concentration should be uniform. Okay, and we have also understand this. I will make you understand the performance equation of the CSTR, right? So in order to calculate the volume of the CSTR, like how much volume of the CSTR we required in order to achieve the desired conversion of 90%, right? Then how we can calculate? So by using the design equation or the performance equation of the CSTR, we have calculated the desired volume of the CSTR, which comes out to be 187.5 cubic decimeter, right? Which means we required 187.5 cubic decimeter volume of CSTR in order to achieve the desired conversion of 90%, right? Okay, now this much volume we required, but then now the next question was like, what will be my reaction time, how much time will it require in order to achieve the desired conversion of 90%, right? Where we have kept all the operating parameters to be constant. We were solving for the first order reaction kinetics for the given rate law minus R is equal to Kca by E, okay? And where the single where we have a single reaction where reactants A are getting converted into the new product B, right? So by using the fundamental concept of the space-time, right? The space-time is defined as the ratio of volume to its volumetric flow rate. It's called the space-time, right? We have calculated the reaction time, okay, which comes out to be 12.5 hours, which means if we select the reactor model as CSTR, then in order to achieve the 90% conversion, we required 187.5 cubic decimeter volume of the CSTR and 12.5 hours of space time, reaction time, right, in order to achieve the 90% conversion, right? I hope you understood, okay? Now, the second reactor model is PFR, plug flow reactor, right? So I will make you understand in the previous lecture the fundamental principle of the plug flow reactor, right? The plug flow reactor is a hollow reactor. Plug flow reactor is a tubular reactor, right? In which we have a hollow space, okay, of the tubular reactor, right? Which means the fluid will flow through the hollow space of the tubular reactor and the reaction will takes place, okay? So now, in order to design the volume of the plug flow reactor, we have used the performance equation of the plug flow reactor, right? So by using the concept of the performance equation of the plug flow reactor, we have calculated the required volume, which comes out to be 48 cubic decimeter, right? And by using the fundamental concept of the space-time, we have calculated the reaction time, okay, which comes out to be 3.2 hours, which means in order to achieve the desired conversion of 90% for the first order reaction kinetics for the given rate law minus RE is equal to Kca, where we have a single reaction, the reactants A are getting converted into the new product, and where we have kept all the operating parameters to be constant. And by selecting the plug flow reactor, we required 48 cubic decimeter volume of the plug flow reactor and 3.2 hours reaction time in order to achieve the desired conversion of 90%, right? I hope you understood, right? Okay, now in plug flow reactor, I have also make you understand that in the plug flow reactor, at the inlet portion of the plug flow reactor, right, at the inlet stream of the plug flow reactor, where we have the highest concentration of the reactants present at the inlet part of the plug flow reactor, right, which means due to the first order reaction kinetics, where we have the concentration is in direct proportionality to the reaction rate. So due to the highest concentration present at the inlet part of the inlet portion of the plug flow reactor, we will have the higher rates of the reaction, right? So due to the higher rates of the reaction, there will be a very good conversion of reactants into the product, right? And along the length and volume of the plug flow reactor, the concentration of reactant will slowly and gradually decrease, right? Due to which the reaction rate will also slowly and gradually decrease, right? I hope you understood. And at the outlet stream of the plug flow reactor, where we have minimal concentration of unreacted reactant presence, or there might be possible that all the reactants have already been converted into the new products, so there are no reactant left at the outlet stream of the plug flow reactor, which means the reaction rate at the outlet stream of the plug flow reactor may slowly, gradually and decrease, or 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 the reaction already completed. Why? Because we are not left with any reactor molecules present in the reaction environment, right? And reaction comes to the completion, right? I hope you understood, right? So here we have completed the second reactor model, PFR, right? Okay. Now the third reactor model is batch reactor. So batch reactor, I make you understand in the previous lectures. Okay, the batch reactor, by using the batch reactor, where we have where the outlet stream of the batch reactor is kept close. Okay, we feed all the feed mixer we feed all the feed mixer to the reaction environment of the batch reactor in a single go, right? And finally, after the feeding all the feed mixer to the reaction environment of the batch reactor, we finally close the inlet stream. Okay, so now there will be no inlet stream and there will be no outlet stream. The inlet stream and outlet stream remain closed during the run of the reaction. Okay. is called the batch reactor. I hope you have understood, right? If you want to recall, I request you to please watch the previous lectures, right? So now, in order to design, now the question was for the first order reaction kinetics for the given rate law, right? In order to achieve the desired conversion of 90% by keeping all the operating parameters to be constant, then how much volume, right? How large volume of the batch reactor be required in order to achieve the desired conversion of 90%, right? And the second question was, what will be my reaction time, right? How much time we will require in order to achieve the desired conversion of 90% by using the batch reactor, right? So by using the performance equation of the batch reactor, we have calculated the time required in order to achieve the desired conversion of 90%, right? Which comes out to be 3.2 hours, right? Okay, so by using the performance equation of the batch reactor, we have calculated the time required to achieve the desired conversion of 90%. Okay, now I will make you also understand that from the performance equation of the batch reactor, how we have derived the volume equation in order to calculate the volume of the batch reactor, right? So by modifying the performance equation, we have derived new equation, right? The new volume equation, okay, in order to calculate the volume of the batch reactor, right? So by using that equation, we have calculated the volume of the batch reactor, which comes out to be 48 cubic decimeter, right? Which means by using the batch reactor, we required 48 cubic decimeter of volume and 3.2 hours of reaction time in order to achieve the desired conversion of 90%, right? Where we have the first order reaction kinetics with the given rate law minus RE is equal to KCA, and where we have kept all the operating parameters to be constant, right? I hope you have understood. Okay, so here we have completed the understanding of the third reactor model. Okay, now let's say the fourth reactor model is PBR, packed bed reactor. Okay, so packed bed reactor. Okay, so I will also make you understand the fundamental principle of the packed bed reactor, right? How the packed bed reactor differs from the plug flow reactor. Okay, packed bed reactor is also a tubular reactor, right? Plug flow reactor is also a tubular reactor. The principal difference between the packed bed reactor and the plug flow reactor is the hollow space of the tubular reactor is completely packed with the different packing materials. The packing materials can be a solid support, solid inert catalyst, a solid catalyst, solid support, solid inert materials, right? By which we tightly pack the packing materials, okay? And the solid bed is generated in the hollow space of the tubular reactor. So it is termed as the packed bed reactor, right? Where we'll carry solid fluid reactions, right? Okay, I hope you understood. And in the case of plug flow reactor, where the entire hollow space of the tubular reactor is kept empty, right? Okay, and the fluid will pass through the hollow space of the tubular reactor and the reaction will take place, right? Okay, so now so the question was, how large volume of packed bed reactor we required in order to achieve the desired conversion of 90%, right, for the first order reaction kinetics? And the second question was, how large, what will be my reaction time in order to achieve the desired conversion of 90%, right? So let's say, so I have make in the previous lecture, lecture number 16, I have make you understand the actual method to calculate and design the volume of the packed bed reactor, right? If you want to recall, I request you to please watch the previous lecture, lecture number 16, right? So I have made you understand the actual method by which we have designed the volume of the packed bed reactor, right? So by using the volume by using the equation of the volume of the packed bed reactor, right, which is defined as the volume of the packed bed reactor is the ratio of the weight of the catalyst and divided by the density of the density, right? Bulk density, right? Okay, the bulk density is the ratio of the weight of the catalyst divided by the total volume occupied by the catalyst, right? Okay, I hope you have understood, right? So by using the actual method in order to design the packed bed reactor, right? So which we have used in order to identify, in order to design how large volume of packed bed reactor we required in order to achieve the 90% conversion, right? So by using that method, we have obtained the volume of the packed bed reactor, which comes out to be 1,72,700 cubic decimeter volume of the packed bed reactor we required in order to achieve the desired conversion of 90%. Okay, and by using the fundamental concept of the space time, we have calculated the reaction time, right? How much time do we require by using the packed bed reactor in order to achieve the desired conversion of 90%, right? Which comes out to be 11,513.333 hours, right? Okay. Okay, I hope you have understood, right? And by using the performance equation of the packed bed reactor, we have calculated how much weight of the catalyst do we require in order to achieve the 90% conversion, right? So by using the performance equation of the packed bed reactor, we have calculated the weight of the catalyst, which comes out to be 1.727 into 10 to 5 kg catalyst, right? Which means we required this much huge amount of catalyst, right, and huge volume to accommodate all the catalysts, right? And we required a very larger reaction time in order to achieve the desired conversion of 90%, right? I hope you have understood. Okay, so now we'll understand the engineering conclusion. Okay, so I will make you understand the engineering conclusion in a very simple and systematic manner, right? So let's say, firstly, I'm comparing two reactor models, CSTR and PFR. Okay, so let's say we can observe, we can analyze that if I use CSTR, right? Remember that we have kept all the operating parameters to be constant, right? We are solving for the first order reaction kinetics, right? For the given rate law minus RE is equal to KCA by using the second form of CA, right? Which is defined as the fundamental relationship and also defined as the conversion. We have used the concept of the space time, right? So if I select CSTR as the reactor model, then in order to achieve the 90% conversion, we required 187.5 cubic decimeter volume of the CSTR and 12.5 hours of reaction time. Okay, now in place of CSTR, what if I use plug flow reactor, right? So let's say if I select plug flow reactor, right, then we required 48 cubic decimeter volume of the plug flow reactor and the 3.2 hours of reaction time, which means in comparison, in the first comparison where I have compared CSTR with PFR, then we can see clearly observe that we required lesser volume and lesser reaction time in order to achieve the desired conversion of 90%, right? So due to those reasons, we will select PFR as the reactor model, right, in which we required lesser volume of 48 cubic decimeter as compared to the CSTR larger volume, and we required lesser reaction time of 3.2 hours in comparison to the CSTR reaction time, which is 12.5 hours, right? So in order to conclude, in the first comparison, we will select PFR as the reactor model, right, where we required smaller reactor volume and lesser reaction time in order to achieve the desired conversion of 90%, right? I hope you understood. Okay, now I will make the second comparison between the plug flow reactor and the batch reactor. Now here it is the twist, right? Now it is becoming more interesting, right? So let's say here we can observe that if I use plug flow reactor and batch reactor, we required same reactor volume of 48 cubic decimeter, right? We have same reactor volume of 48 cubic decimeter. So how? We need to understand that. Okay, if I use plug flow reactor in batch or a batch reactor, we required same reaction time of 3.2 hours. Okay, so it is very interesting, right? If we are changing the different reactor models from plug flow reactor to batch reactor or from batch reactor to plug flow reactor, then we require same reactor volume and we require same reaction time. So how it is so? We need to understand that, right? So it is very interesting. Okay, so let's say the plug flow reactor. So let's say the plug flow reactor in which at the inlet part we have the highest concentration of the reactant presence, right? So due to the highest concentration of the reactant present at the inlet part, okay, due to the direct proportionality sign of concentration with the reaction rate, we'll have the highest reaction rate at the inlet portion of the plug flow reactor. And with respect to the length and volume of the plug flow reactor, the concentration of the reactants slowly and gradually decrease, right? So due to which the reaction rate also slowly and gradually decrease along the length and volume of the plug flow reactor, right? And at the outlet portion of the plug flow reactor, where we have minimal concentration of unreacted reactants presence, or there are chances there are no reactant presence in the reaction environment, right? Due to which the rate of the reaction will also decrease along the length and volume of the packed bed reactor. Okay, I hope you have understood. Okay, now we'll understand the batch reactor. Now, and what happens in batch reactors, right? So let's say here I'm stating that the batch reactor is the batch reactor behaves as a time-based PFR, right? So remember, right? Understand carefully. I'm stating that the batch reactor is time-based PFR. So what does it mean? We need to understand that, right? So let's say, so how we'll understand that, right? So in the batch reactor, at the initial start of the reaction or the before reaction, first we feed all the feed mixture to the reaction environment of the batch reactor, right? And afterwards, after completing the feeding of the feed mixture to the reaction environment of the batch reactor, we close the inlet stream of the reactor, right? And outlet stream is remain closed. Okay, now the reaction will takes place, right? Now reaction will start. So at the initial start of the reaction, right, we are using the batch reactor, right? So at the initial start of the reaction, we'll have the highest concentration of reactants present in the reaction environment of the batch reactor, which means now here we are using the same first order reaction kinetics. We are using the same rate law, which is minus Ra is equal to Kca, which means at the initial start of the reaction, right, in the reaction environment, we have the highest concentration of reactants presence, right? So due to the highest concentration of the reactant present at the initial start of the reaction in the batch reactor, okay, and due to the first order reaction kinetics, we have the direct proportionality sign of concentration with the reaction rate, right? Which means at the initial start of the reaction, due to the presence of higher concentration of reactants at the initial start of the reaction, we will have the higher rates of the reaction, right? As alike with the plug flow reactor. At the inlet stream of the plug flow reactor, we have the highest concentration of reactant presence, right? Due to which the reaction rate also increases, right? So both are same. Okay, I hope you have understood. Now let's come back to the batch reactor. So let's say now the reaction has started, right? Now during the progress of the progress of the reaction time, what will happen? Slowly and gradually, the concentration of reactants in the reaction environment of the batch reactor will slowly and gradually will decrease, right? The reactants will get converted into the new products, right? Which means with the progress of the reaction, the concentration of the reactants slowly and gradually decreases, which means due to the first order reaction kinetics, due to the direct proportionality of reaction rate with the concentration, with the progress of the reaction in the batch reactor, the concentration of the reactants is decreased, right? Due to which the reaction rate will also decrease with the progress of the reaction, right? Okay, now compare with the plug flow reactor. Along the length and volume of the plug flow reactor, the concentration of the reactants is slowly gradually decreasing, right? Which means due to the decrease in the concentration, the rate of the reaction also decreases due to the direct proportionality sign present in the first order reaction kinetics in the rate law, right? Okay, so same way the batch reactor will also behave. Okay, I hope you understood. Okay, now let's come back to the batch reactor. Now let's say after after few after some reaction time, now let's after three okay, so near about to the end of the reaction time, near about at the end of the reaction time, where all the reactants have utilized, right? Okay, and there will be presence of only few reactant molecules remains unreacted, okay, in the reaction environment. Okay, and up to which we have already achieved the 90% conversion, right? Which means which means we have the presence of very low concentration of the reactants presence, right, in the end of the reaction, okay, or in the batch reactor, due to the presence of lower concentration of reactants in the reaction environment of the batch reactor, the rates of the reaction rate will also decrease with the progress of the reaction time. Okay, I hope you have understood. So same way, if we compare with the plug flow reactor at the outlet stream of the plug flow reactor, where we have the minimal concentration of reactants remains, right, due to which the rate of the reaction will also decrease, right? Okay, so due to those reasons, we can say that the batch reactor will behave like time-based PFR, right? I hope you understood. Okay, the batch reactor will behave as a time-based PFR, right? So due to those reasons, if we see due to those reasons, both the reactor models, PFR and the batch reactor, have, right, for the first order reaction kinetics, right, both the reactor models, PFR and batch reactor, will behave same, will require same reactor volume of 48 cubic decimeter and same reaction time of 3.2 hours in order to achieve the desired conversion of 90%, right? I hope you understood. Okay, now, but the question is, which reactor model do we select? Plug flow reactor is superior, or the plug flow reactor is preferred, or batch reactor is preferred? Which reactor we need to select? Okay, so let's say, so here we will understand that we have two types of reactors: continuously flow reactors and the batch reactors. Continuously flow reactors are CSTR, plug flow reactors, and packed bed reactors are continuously flow reactors. Batch reactor is only we have one batch reactor, right? Which means continuously flow reactors, which means there will be a continuously feeding of the feed mixer to the via inlet stream of the reactor, right? Which means we will have continuously feeding of the feed mixer via inlet stream to the reactor. And continuously in the reaction environment of the reactor, continuously the reaction will take place. Okay, and there will be a transformation of reactants into the product. Okay, and the conversion will achieve. Okay, and continuously the formed products will exit through the outlet stream of the packed bed, will exit through the outlet stream of the reactor, right, continuously, which are called the continuously flow reactors. But in the case of batch reactor, where we have the outlet stream remains closed, we'll feed all the feed mixer once in a single go in the to the reaction environment of the batch reactor, right? And after that we will close the inlet stream. Okay, and there will be no inlet stream and there will be no outlet stream. Okay, now the reaction will take place, and after the formation of the desired product, and after achieving the desired conversion, we will open the outlet stream of the batch reactor, and we will take out all the formed product out of the batch reactor via outlet stream, right? Which means if we select continuously flow reactor, right, so in the second comparison we have one continuously flow reactor, which is plug flow reactor, and we have batch reactor, right? So if we select, in order to increase the manufacturing of the chemicals, in order to increase the productivity, okay, we will select and we will prefer continuously flow reactor, right, which is plug flow reactor, in comparison with the batch reactor, right? Why? Because if we select batch reactor, then there is an increase in the operational cost, right? There is increase in the maintenance. Okay, so due to those reasons, right, and which will consume more time, right? Okay, so due to those reasons, we will always prefer, okay, we try to prefer the plug flow reactor. Okay, I hope you understood. Now I will make the third comparison between CSTR PFR batch reactor at one side and against the packed bed reactor, right? The third comparison is between CSTR PFR and plug flow reactor at the one side, comparing with the packed bed reactor. Okay, so let's understand that it will be more interesting, right? So here you can see that as compared to the other three reactor models, the packed bed reactor requires very large volume of the reactor, right? So we can see the CSTR requires 187.5 cubic decimeter, plug flow and batch requires 48 cubic decimeter volume of the reactor, right? But if we select packed bed reactor, then we require 1,72,700 cubic decimeter of the volume, which is a very huge volume, right, in comparison with the other three reactor models. Okay, now if we compare it with the reaction time, we can say that if we select packed bed reactor, then we required very huge reaction time of 11,513.333 hours, right, as compared to the other three reactor models. Okay, so which is a very huge reaction time. Okay, and another thing, an add-on is we required very large volume, very huge amount of catalyst, right, which is 1.727 into 10 to 5 kg of catalyst we required in order to achieve the desired conversion of 90%, right? Okay, so it is very huge, right, which means if we select the packed bed reactor, then we required a very huge weight of the catalyst, we required very large reactor volume, we required very larger reaction time, okay, as compared to the other three reactor models, right? So why it is so? Due to the smaller rate constant value, okay, due to the smaller rate constant value, the reaction rate also decreased, right, due to which the volume of the packed bed reactor increased, the weight of the catalyst also increased, and due to which the reaction time also increased, right? Okay, so in comparison with the of packed bed reactor with the other three reactor models, we will try to select any out of three reactor models. We'll try to select any one reactor model, right? But okay, why? Because if we select packed bed reactor, then we require a very large volume of the reactor and very longer reaction time, okay, so which is not beneficial, right? Okay, so due to those reasons we will not select packed bed reactor. I hope you have understood. Okay, now the fourth comparison is, now what if from these three reactor models, which reactor model we will prefer, right? Okay, which reactor model we will give the best priority? Okay, the answer is by, so here we can observe that if we from the CSTR and PFR we require a very smaller reactor volume and smaller reaction time of 3.2 hours and smaller reactor volume of 48 cubic decimeter, right, with comparison to the CSTR, right? So we will, in order to conclude the engineering conclusion, we will select plug flow reactor, right, in which we required 48 cubic decimeter of reactor volume and 3.2 hours of reaction time. Okay, I hope you understood. Okay, so here finally I will make you understand the engineering conclusion for the first order reaction kinetics, right? Okay, now so I request you to please make all the notes, right? Okay, so now we are dwelling more deeper into the fundamental understanding of the first order reaction kinetics, right, where we have the given rate law as minus Ra is equal to Kc. Okay, so here you can see that the reaction rate is in direct proportional to the rate constant and Ca, right, concentration. Okay, now let's say we'll make the detailed comparison between the reaction rate minus Ra, the rate constant, K, the concentration of reactants, Ca, the volume of the reactor, with the volume of the reactor and with the reaction time. So we'll make detailed comparison between all these parameters, right, all these variables. Okay, so it will be more interesting to understand in the depth for the first order reaction kinetics, right? So let's understand that. So for the first order reaction kinetics, for the given rate law minus Ra is equal to Kca, where we have the direct proportionality of reaction rate with the rate constant K and the concentration of reactant Ca. Okay, now what if in the first part, now we'll understand the first part, right? What if I keep the rate constant to be constant? Okay, so understand carefully. Okay, so what if I keep rate constant to be constant, then how will it affect on the reaction rate and the concentration? Okay, and how will it affect on the volume of the reactor or the reaction time? We'll understand that. Okay, so if we keep the rate constant value to be constant, okay, now what if I increase my concentration of the reactants in the concentration of the reactants present in the reaction environment of the reactor, right? So what if I increase the concentration of the reactants, then how will it affect the reaction rate and the volume of the reactor and the reaction time? So by increasing the concentration of the reactants present in the reaction environment of the reactor, right, due to the first order reaction kinetics, where we have the given rate law has minus Ra is equal to Kca, where we have direct proportionality with the reaction rate with the concentration, which means if we increase the concentration, right, which means if we increase the concentration, then the reaction rate will also increase due to the direct proportional design, right, due to which, so okay, so by keeping the rate constant value to be constant, if we increase the concentration of reactants present in the reaction environment due to the direct proportional design, the reaction rate will also increase. Okay, I hope you have understood. Okay, now by increasing the concentration of the reactants, okay, so the rate of the reaction increase, right? So the rate of the reaction increase, which means the speed of the reaction increase, right? So due to the increase in the speed of the reaction, we will require very smaller volume of the reactor and lesser reaction time in order to achieve the desired conversion, right? Okay, so due to those reasons, we require a very smaller volume of the reactor and the reaction time also decrease, right? So I hope you have understood the first part. Now we will understand the engineering interpretation for the first part, right? Now, so this phenomena will occur when we increase the concentration of reactants present in the reaction environment, right? So by increasing the concentration present in the reaction environment, the reaction rate will also increase. The increase in the reaction rate, which means the speed of the reaction will increase, right? Due to which we require smaller reactor volume and lesser reaction time in order to achieve the desired conversion, right? Okay, so I hope you have understood the first part. So here we have completed the understanding of the first part. Now we'll understand the second part. What if again I am making the constant as rate constant, right? So I'm keeping rate constant to be constant. Okay, now what if I decrease the concentration of the reactants in the reaction environment of the reactor, then how will it affect to the reaction rate, the volume of the reactor and the reaction time? We'll understand that. Okay, so by decreasing the concentration of the reactants present in the reaction environment of the reactor, and we have the first order reaction kinetics, where we have the rate law has minus Ra is equal to Kca, where the reaction rate is in direct proportionality to the concentration, right? Which means if we decrease the concentration of reactants present in the reaction environment of the reactors, the reaction rate also decreases, right? Which means the decrease in the reaction, due to the decrease in the concentration, the reaction rate decreases, right? The reaction rate decreases, which means the speed of the reaction decreases, right? So due to the decrease in the speed of the reaction, okay, due to the decrease in the reaction rate, okay, we required very larger volume of the reactors and larger reaction time in order to achieve the desired conversion, right? I hope you have understood, right? So by decreasing the concentration, okay, so now we'll understand the engineering interpretation, right? Which means by decreasing the concentration, the reaction rate also decreases, and we require larger reactor volume and larger reaction time in order to achieve the desired conversion. Okay, I hope you have understood. Okay, so here we have completed the understanding of the second part. Now we'll understand the third part, right? So let's say the third part, in which, let's say, now what if I make the concentration to be constant, right? Now we have two variables, which is reaction rate and rate constant, right? So what if I make the concentration to be constant, then how will it affect on the reaction rate and the rate constant, and how will this affect on the volume of the reactor and the reaction time, right? So let's understand that. So let's say by keeping the concentration to be constant, right? Now what if I increase the reaction rate, right? So let's say by keeping the concentration to be constant, but now what if we increase the rate constant, right? So let's say if we increase the rate constant, due to the first order reaction kinetics, where we have the given rate law has minus Ra is equal to Kca, where we have direct proportionality of reaction rate constant with the reaction rate, right? Which means if we increase the reaction rate constant, then the reaction rate will also increases, right? Which means the reaction rate will also increases, right? Which means the speed of the reaction has increased, right? So due to increase in the reaction rate, the speed of the reaction has increased, due to which we will require smaller volume of the reactor and will require lesser reaction time. Okay, I hope you understood, right? Now we'll understand the engineering interpretation for the third part. Okay, so let's say this phenomena we will observe when we kept the concentration to be constant. Okay, okay, so this phenomena is observed when the temperature of the reaction environment is increased. Okay, I repeat, this phenomena we observe when we increase the temperature of the reaction environment of the reactor, right? So by increasing the temperature of the reaction environment, the reaction rate constant will also increase. Okay, so due to the increase in the temperature, the reaction rate constant will also increase, due to which, due to the direct proportionality sign for the first order reaction kinetics, okay, due to the increase in the temperature, the reaction rate reaction rate constant increases, due to which the reaction rate also increases, right? Which result into requirements of the smaller reactor volume and lesser reaction time. Okay, I hope you understood. Okay, so here we have completed the understanding for the third part. Now we'll understand the fourth part. Now again, what if I kept the concentration to be constant? Then how will it affect on the reaction rate and the rate constant, and how will it affect on the volume and the time, right? So let's say if I keep the concentration to be constant, now what if the rate constant is decreased, right? Then how will it affect on the reaction rate and the volume and reaction time? We'll understand that. So okay, so by keeping the concentration to be constant, now what if I decrease the reaction rate constant, right? If I decrease the rate constant value, right, we have the direct proportionality sign for the first order reaction kinetics, right? Which means if I decrease the reaction rate constant value, the reaction rate also decreases, right? Which means the speed of the reaction decreases, right? Okay, which means we will require very larger reactor volume in order to achieve the desired conversion. Okay, and will require larger reaction time in order to achieve the desired conversion, right? I hope you have understood, right? Now we'll understand the engineering interpretation, okay, of the fourth part. So this phenomena will observe when the temperature of the reaction environment is decreased, right? This phenomena will observe when the temperature of the reaction environment is decreased, right? Which means by decreasing the temperature of the reaction environment of the reactor, the rate constant will decrease, right? Due to the decrease in the temperature, the rate constant value will decrease, right? So due to the decrease in the rate constant value, we have the direct proportionality sign with the reaction rate, which means due to the decrease in the reaction rate constant, the reaction rate will also decreases, right? Due to which the speed of the reaction decreases, right? Now in order to achieve the desired conversion, we required very larger volume of the reactors and we required very larger reaction time in order to achieve the desired conversion, right? I hope you understood, right? Okay, now let's say, so here we have completed the understanding of the fourth part. Okay, I hope you understood. Okay, now let's say we'll understand the sixth part. Okay, so now let's say, what if I increase the rate constant? Okay, and what if I also increase the concentration? Then how will it affect on the reaction rate and volume and reaction time, right? Volume of the reactor and the reaction time. We'll understand that. Okay, so let's say if I simultaneously increase the rate constant value and the concentration of reactants present in the reaction environment, right? Okay, so due to the direct proportionality sign for the first order reaction kinetics, where by increasing simultaneously rate constant value and the concentration value, okay, the reaction rate will strongly increase, right? The reaction rate will strongly increase, right? Okay, due to the strong increase in the reaction rate, the speed of the reaction will become so fast, right? Which means within a few seconds or milliseconds, the reaction will achieve the desired conversion and will achieve the desired selectivity of the product, right? Which means we will require a very smaller reactor volume, which means due to the increase in the rate constant value, okay, and due to the also simultaneous increase in the concentration of the reactants present in the reaction environment, okay. So due to the simultaneous increase in both rate constant value as well as the concentration value, which will result into the strongly increase in the reaction rate, right? Which means if there is a strongly increase in the reaction rate, which means the speed of the reaction become so fast, right? Which means we'll require very smaller reactor volume, okay. So we'll have strongly decrease in the volume of the reactor, right? So due to increase in the speed of the reaction, right, within microseconds, the reaction will tends to complete, right? Okay, so due to those reasons, we'll require a very small reactor volume and will require very lesser reaction time of few seconds or few microseconds, right? And we'll achieve the desired conversion, right? So I hope you have understood. Okay, so there will be strongly decrease in the volume of the reactor and strongly decrease in the reaction time. Okay, I hope you have understood. Now we'll understand the engineering interpretation for the fifth part, right? Okay, so this phenomena is observed when there is an increase in the concentration, right? This phenomena is observed when there is an increase in the concentration of the reactants present in the reaction environment. Also, there is an increase in the temperature of the reaction environment, right? Which means due to the increase in the concentration of the reactants environment present in the reaction environment of the reactor, and simultaneously due to the increase in the temperature of the reaction environment of the reactor, we right, so simultaneously the concentration also increase and the temperature of the reaction environment also increase, right? Due to which the rate constant will also increase, right? So due to the increase in the rate constant value, the reaction rate will also increase, right? Which means here the concentration is also increasing, right? Concentration of reactants is also increasing. The temperature of the reaction environment is also increased, due to which the rate constant value also increase, right? So due to this simultaneous effect of increasing temperature, concentration, and reaction rate constant value, the reaction rate will strongly increase, right? Okay, so due to those reasons, there will see that there will be very strongly decrease in the requirement of the volume of the reactors and strongly decrease in the reaction time. Okay, in within a few seconds, microseconds, in a very smaller reactor volume, we will achieve the desired reactor volume. Okay, I hope you understood, right? So here we have completed the understanding for the fifth part. Now we will understand the sixth part. Now what if the concentration of the reactants decrease in the reaction environment? Then how will it affect, right, to the other reaction parameters? Okay, now what if simultaneously the reaction rate constant value decreases, right? Which means what if there is a simultaneously decrease in both the concentration of the reactants and the rate constant value, right? Then how will it affect to the reaction rate and volume of the reactor and the reaction time? Let's understand that, right? So due to the direct proportionality sign of the reaction rate with the rate constant value and the concentration of the reactants, now due to the simultaneously decreasing of the concentration and the reaction rate constant, the reaction rate also strongly decrease, right? Okay, which result into the requirement of the larger reactor volume, right? The reactor volume will become so large, okay, and will require larger reaction time, right? So this case we can, okay, so this case we can see we can compare with the packed reactor, right? So due to the decrease in the concentration, due to decrease in the rate constant value, right, the reaction rate also decreases, right? Due to which we required a very huge weight of the catalyst, right? And we required very huge volume of the reactor, right? See, the volume of the reactor strongly increased, the reaction time strongly increased, right? So you can see we required a huge reaction time of 11,513.33 hours, right? And we require very huge volume of 1,72,700 cubic decimeter, right? If we use packed reactor, right? So I hope you understood the sixth part, right? Now we'll understand the engineering interpretation for the sixth part. Okay, now this phenomena will observe when there is a decrease in the concentration of the reactants present in the reaction environment of the reactor, right? So due to the decrease in the concentration of the reactants present in the reaction environment, and simultaneously due to also decrease in the temperature of the reaction environment, the rate constant value will also decrease, right? So due to decrease in the temperature, the concentration of reactants and the rate constant value will see that the reaction rate will also strongly decrease, right? Which result into the requirement of the larger reactor volume and longer reaction time in order to achieve the desired conversion. Okay, I hope you have understood the sixth part, right? So here we have completed the understanding of the sixth part. Now in the seventh part, what if I make the rate constant to be constant? What if, right? And then how will it affect the reaction rate constant and concentration, right? So in the seventh part, I am making the reaction rate to be constant. Okay, so how will it affect on the rate constant and the concentration and volume and the reaction time, right? So let's understand that. So in the seventh part, I have made the rate constant, reaction rate to be constant. Okay, now what if I increase the rate constant value, right? So due to the direct proportionality design, if I increase the rate constant value, the reaction rate will also increase. Okay, but now what if I simultaneously decrease my concentration, right? Okay, now understand carefully. Okay, so see in the first part, here in the first case, I have increased my rate constant value. Okay, and simultaneously I am decreasing the concentration, which means due to the opposite effect present at the same time, right? At the same time we are increasing the rate constant value and simultaneously we are also decreasing the concentration, right? Which will result into the constant reaction rate, okay, which will nullify, okay, because simultaneously we have two opposite effects, right? In the first effect where we are increasing the rate constant value, and in the another effect where we are decreasing the concentration value. So due to these two opposite effects, the it becomes nullified, right? And due to those reasons, the rate constant, due to those reasons, the reaction rate will remain constant, right? So due to those reasons, we can observe that there might be a slight increase in the volume of the reactor and reaction time, or there is possible that the volume of the reactor and the reaction time remains constant due to the constant reaction rate, right? I hope you have understood. Okay, now we'll understand the engineering interpretation for the seventh part. Okay, so let's say here this phenomena will observe when there is a decrease in the concentration of the reactants present in the reaction environment of the reactor. Okay, but this increase in the rate constant will observe when will increase the temperature of the reaction environment of the reactor, right? So by increasing the temperature of the reaction environment of the reactor, the rate constant value will increase, right? So due to the increase in the temperature, the rate constant value increases, right? Due to which okay, and simultaneously the concentration of the reactants also decreasing, right? Which means the reactants are getting consumed and are getting transformed into the new product, right? So due to the simultaneous effect of increasing in the rate constant value and the decreasing in the concentration, we will remain where we will have the constant reaction rate, okay, and due to which we will have constant reactor volume and reaction time, or there might be possibility of slightly increase in the volume and the reaction time, volume of the reactor and the reaction time. Okay, I hope you have understood. Okay, so here we have completed the understanding of the seventh part. Now we'll understand the eighth part. Okay, now again, what if I keep reaction rate to be constant, okay, which means the speed of the reaction is constant, right? In the second part, we have also kept the reaction rate to be constant, which means the speed of the reaction remains constant. Okay. In this eighth part, again, I am keeping the reaction rate to be constant. Okay. Now, what if in place of increasing the rate constant value, what if I decrease the rate constant value? And what if I increase the concentration of the reactants present in the reaction environment of the reactor? Okay, then how will it affect? Okay, we'll understand that. So let's say, so again here, simultaneously, two opposite effects are taking place, right? The first one is we are increasing the concentration of reactants present in the reaction environment of the reactor, right? And second is we are decreasing the rate constant value, right? So due to these two opposite effects, which will nullify, and due to those reasons the reaction rate will remain constant, right? I hope you have understood. Okay, so due to this reason we will observe that we will have the constant reactor volume and reaction time, or there might be possibly in slightly increase in the volume of the reaction time due to, okay, due to the reaction rate remains constant. Okay, I hope you understood. Okay, now we'll understand the engineering interpretation for the eighth part. Okay, now this phenomena will observe when there is an increase in the concentration. Okay, there is an increase in the concentration of the reactants present in the reaction environment of the reactor. Okay, but the decreasing in the rate constant value will observe when the temperature of the reaction environment is decreased, right? Will observe. Okay, so I repeat, the decrease in the reaction rate constant value will observe when the temperature of the reaction environment is decreased, right? Due to the decrease in the temperature of the reaction environment, the rate constant value will also decrease, right? Okay, and simultaneously we are increasing the concentration of the reactants, okay, presence in the reaction environment of the reactor. So due to these two opposite effect, the rate constant, the reaction rate will remain constant, right? Okay, I hope you understood, right? So due to those reasons the reactor volume will remain constant and reaction time will also remain constant, or there might be possibility of slightly increase in reactor volume and the reaction time. I hope you understood. So here we complete the understanding of the eighth part. Okay, now we'll understand the ninth part. Okay, so let's say now we'll understand the ninth part. Okay, in the ninth part, now what if I increase the reaction rate and simultaneously I'm also increasing the rate constant value? Okay, so let's say, let me make it clear that, let's say in the ninth part, by increasing the rate constant value, okay, and by slightly decreasing the concentration. Okay, so please listen carefully. Okay, so let's say in the ninth part I am increasing the rate constant value and I am slightly decreasing the concentration, right? This down arrow indicates the slight decrease in the concentration. Okay, so there is a very minimal decrease in the concentration. Okay, but simultaneously we are increasing the reaction rate constant. Okay, so due to the increase in the reaction rate constant, the rate or reaction rate will also increase, right? The reaction rate will also increase. Okay, due to those reasons the volume of the reactor will require very slow, right? The volume of the reactor will decrease due to the increase in the reaction rate. The speed of the reaction has increased, due to which we will require smaller reactor volume and lesser reaction time in order to achieve the desired conversion, right? Okay, or there might be possibility of reactor volume and reaction time to remain constant. Okay, I hope you understood. Okay, now we'll understand the engineering interpretation for the ninth part. Okay, so this phenomena will observe when the temperature of the reaction environment is increased, right? So when we increase the temperature of the reaction environment, there will be an increase in the reaction rate constant value, right? So due to the increase in the temperature of the reaction environment, the rate constant will also increase, right? Due to which the reaction rate will also increase. Okay, and there will be a very slight decrease in the concentration of the reactants present in the reaction environment, right, which will result into the requirements of the smaller reactor volume, or the volume may remain constant and will which result into the lesser reaction time, or the reaction time may remain constant, right. I hope you understood. Okay, so here we have completed the understanding of the ninth part, right. Now we'll understand the 10th part. So in the 10th part, now again, what if we decrease the reaction rate constant, right? So due to the direct proportional design, if we decrease the reaction rate constant, the reaction rate will also decrease, right? But simultaneously, we are slightly increasing the concentration. So please remember this. Please understand carefully, right? The reaction rate constant value is decreased, due to which the reaction rate will also decrease, right? And there is a slight increase in the concentration. Okay, so due to this effect, okay, so due to the decrease in the reaction rate, okay, which means the speed of the reaction decreases, okay, due to which will require larger volume of the reactors in order to achieve the desired conversion, and will require longer reaction time in order to achieve the desired conversion. Okay, or there might be possible that the reactor volume and reaction time may remain constant. Okay, okay, so we'll understand the engineering interpretation for the 10th part. So this phenomena will observe when there is an increase in the slightly increase in the concentration of the reactants present in the reaction environment, and the reaction rate constant will decrease, right? So let's say, so when the reaction rate constant will decrease, right? So when there will be a decrease in the temperature of the reaction environment of the reactor, we will find that due to the decrease in the temperature of the reaction environment, the rate constant value will also decrease, right? Due to those reasons, due to the decrease in the temperature of the reaction environment, the rate constant will decrease, due to which it will result into the decrease in the reaction rate, which means the speed of the reaction will decrease. Due to the decrease in the speed of the reaction, will require larger volume of the reactors in order to achieve the desired conversion, and will require longer reaction time in order to achieve the desired conversion, right? Or there might be possibility of slightly increase in the volume of the reactor and slightly increase in the reaction time, or there might be also a possibility of the reactor volumes remain constant and reaction time also remain constant. Okay, so I hope you understood, right? So here we have completed the understanding of the 10th part. Okay, so in today's lecture, I will make you understand. So in order to conclude the entire lecture, in today's lecture, finally, I will make you understand the engineering conclusion for the first order reaction kinetics, right? Where we have kept all the operating parameters to be constant, okay? And we have used the first order reaction kinetics, where we have given rate losses minus RE is equal to KCA, right? Where we have used different reactor models, CSTR, PFR, batch, and PBR, and we have tried to understand and design the required volume of the reactors, right? So we have tried to understand that how large volume of the reactors we required, okay? What will be my space time or the reaction time, okay? What will be my residence time? How much volume of the reactor, how much weight of the catalyst do we require in order to achieve the desired conversion, right? Followed by where we have made the detailed comparison and detailed understanding of engineering conclusion, right? Where we have compared different reactor models with the reactor volumes, reaction time, okay, and the weight of the catalyst, right? Followed by we have understand in detail, right? We have followed by we have dwelled more deeper into the fundamental understanding of the first order reaction kinetics, right? Where we have compared the reaction rate with the rate constant value, the concentration of reactants with the volume of the reactor and the reaction time. Okay, I hope and we have also understand the engineering interpretation for each and individual parts, right? So I hope you understood. Okay, so I request you to please make all the notes. Okay, and if you have any questions, feel free to comment below. I will try my best to reply to your comments. Okay, so until then, stay focused, keep learning, and stay curious. Thank you for watching my video. Jai Ambe.